Hello, today we are starting chapter 9, which is going to be our last chapter of the year. In chapter 9, we are going to continue to study quadratics. We already looked at how to add, subtract, multiply, divide, factor quadratics, and we used factors to solve quadratic equations. In our first lesson today, we're going to look at how to make the graphs of a quadratic or a second degree equation. And then later in the chapter, we'll look at other methods for solving quadratics that don't factor. So remember, a quadratic function is something that looks like y equals ax squared plus bx plus c. A quadratic always has to have an x squared term, or in other terms, a second degree expression. The standard form for a quadratic is in descending order, so that means a squared, ax squared, then the plain old x, then the plain old number. The graph of a quadratic function is something that's called a parabola. A parabola is a U shape or an upside down U shape that looks like this. Parabolas are always symmetric, meaning that if you fold a parabola in half, the two halves are exactly the same. The line where you would fold a parabola in half to show the two halves that are mirror images is called the axis of symmetry. The axis of symmetry refers to that line, and when we graph our parabolas, an axis of symmetry always has an equation. It's a vertical line, so it'll always have an equation that looks like x equals some x number. When you graph a parabola, you'll also see that we always have a central point. That's called the vertex of the parabola. It's either down at the bottom, the minimum or lowest point, or up at the top, the maximum or the highest point. The vertex always sits on the axis of symmetry. Again, it's the middle point of your graph. When we graph parabolas, we're going to look at some of their characteristics. We've already discussed the next three terms, domain, range, and the y-intercept. Remember, domain is all of the possible x values on the graph. Range is all of the possible y values. And a y-intercept is where your graph crosses over the y-axis. Remember that if you're sitting on the y-axis, your x number is always 0. So our y-intercept will always be a point where the x number is 0, comma, some y number. So take a look at the first two examples down at the bottom here. These two examples have the parabolas already graphed for us. Our job is to look at some of these different characteristics. So when you take a look at question number 1, first we need to identify the axis of symmetry. So when I look at my graph, the axis of symmetry is always going to be the fold line that makes the two halves symmetric. For this graph, imagine you can fold it right along this line here, right down the middle. That line has the equation x equals, and then the x number for that line. Well, this one is at x equals 3. The vertex is either the lowest or highest point on the graph, right in the middle of the graph. So our vertex is this point down at the bottom here. That point has the coordinates 3, comma, -6. And as I mentioned, it's the very bottom of the graph, so this vertex is a minimum. The y-intercept is the point where your graph crosses over the y-axis. This graph hits the y-axis here at this point, which they've kind of highlighted for you. That's the point 0, comma 3. Domain are all of the possible x values. For every single parabola, every quadratic function, the domain is always all real numbers. Remember, that's the fancy R with the extra leg. And then the range are all of the possible y values. The range for each parabola will be different depending upon the graph. So in this graph, the y values go as low as -6, but they never go past -6. If I look at the possible y numbers, The lowest y value, our minimum point, is at -6. Everything else is above that. So our range is going to be the y values bigger than or equal to, greater than or equal to, -6. Let's do the same thing for question number 2. So we start off with our axis of symmetry. That's the line that cuts the graph in half into 2 equal halves. The axis of symmetry always has an equation, x equals some x number. Here, that x value is at 2. The vertex is the central point on our graph, always sits on the axis of symmetry. So the vertex is this point here, which has the coordinates 2, 1. And this vertex is the highest point of the graph. So this vertex is a maximum. Our y-intercept, where the graph crosses over the y-axis, is here. The y-intercept is always 0, and this graph crosses the y-axis at -3. Domain for every parabola is always going to be all real numbers. We could plug in any x value we want. And then the range is dependent upon the picture. So for this graph, our vertex point was the highest point up here at 1. And the rest of the graph has y values below that. So this time our range is going to be the y values less than or equal to +1. Okay, when you flip over to the back, the other examples for today, we are going to create our own graph of a quadratic function. So we're going to make the parabola for a quadratic equation. We always do that by first finding the axis of symmetry. We want to know where's the middle of our graph. And the axis of symmetry has this formula, x equals -b over 2a. A, B, and C are the numbers from the equation, and I'll show you those in number 3. Then we're going to find the vertex, make a table of values so that we can find other points on our graph, plot the points, connect the dots, make sure we put our arrows at the ends. So let's run through all of these steps in question number 3. So it says graph each quadratic function. So first we're going to start by identifying A, B, and C on the equation. Remember, quadratic in standard form is ax squared plus bx plus c. So a is whatever number is in front of x squared. Here we don't see a number, but we know that it must be 1. B is the coefficient of x. So here b is -3. Make sure you take the sign with the number. And c is the constant, the plain old number at the end, which in this case is 2. Okay, we always start by finding the axis of symmetry first, and that has the formula x equals -b over 2a. So for this one, x equals b is -3 over 2 times a is 1. -3 is +3. 2 times 1 is just 2. And 3 over 2 is 1.5, or 1.5. So our axis of symmetry is at x equals 1.5. So we know the middle of our graph is going to be about here. We're then going to use that to help us create a table of values. When we make our table of values, the axis of symmetry, the vertex, really, is always going to be the center of the graph. The vertex is the center of our graph, so it's always going to be the center of our table as well. So I'm going to put in the axis of symmetry that we just found, 1.5. and then choose two values below that x number and two values above. So below 1.5, let's pick 1 and 0. Above 1.5, I'm going to choose 2 and 3. Okay, we're then going to plug each of these x values into our equation to find the matching y value. So if x is 0, when I plug back into the original problem, it tells me y equals 0 squared minus 3 times 0 plus 2. Well, 0 squared is just 0. Negative 3 times 0 is 0. Plus 2 makes the whole thing 2. Then I go back to my equation, plug in. X is 1. So now I have y equals 1 squared minus 3 times 1 plus 2. This ends up being 0. Then I plug in 1.5, so y equals 1.5 squared minus 3 times 1.5 plus 2, and that is 1/4 or 0.25. When we plug in y is 2, 2 squared minus 3 times 2 plus 2 is 0. And when we plug in 3, 3 squared minus 3 times 3 plus 2 equals 2. You may notice that when you take a look at the values we came up with, around our vertex, so around this point in the middle here, notice that the y values are symmetric. They go 2, 0, 0.25, and then 0, 2. They repeat in the opposite order. That will happen every single time as long as you choose points symmetric around the vertex. So if that doesn't happen, there's some kind of mistake. You should go back and look at your numbers. Hey, each row in our table of values now represents a point on the graph. So let's graph our points. So from the first row, our first point is going to be 0, 2. Then we have 1, 0, 1.5, and 0.25, negative 0.25, excuse me. So we're going to do our best to estimate where that point is. It'll be off of the grid lines, which is fine. Then graph the 0.20 and the 0.32. Okay, once we've plotted our 5 points, connect them into something that looks like a U shape. It's not going to be perfect, and that's fine. Just make sure that you're not making something that looks like a V, because that's a graph for a different type of function. Okay, this would be the graph of our quadratic. So we have our axis of symmetry. You can see the vertex down here at the bottom. Because the vertex is all the way at the bottom, it's going to be a minimum, or the lowest possible point. We can also identify the y-intercept here at 0, 2, and look at all of the characteristics we discussed on the front. Okay, if you take a look at example number 4, again, we're going to create our graph. So let's run through each of our different steps. We're going to start by picking out A, B, and C from our given equation. So here, A is the number always in front of x squared, so A is 4. B is in front of x, so B is negative 12. And C is the constant, the plain old number by itself, in this case 3. We use those values to calculate the axis of symmetry. Has the formula x equals negative b over 2a. So here I have x equals negative, b is negative 12 over 2 times a is 4. Negative 12 is positive 12. 2 times 4 is 8. 12 divided by 8 is 1.5. So it just so happens that our axis of symmetry is the same as the last question. That's just a coincidence. Okay, if I graph x equals 1.5 on my graph, it would look about like this. So this should be the center of my parabola. Then we create our table of values. When we create our table of values, the axis of symmetry is going to be in the center of the x numbers. Again, we choose 2 numbers less than that and 2 numbers greater than that. And we take each of our x values, plug them into the formula to find the matching y values. So we plug them into the equation, the original question. If we plug in x is 0, the y value is 3. When you plug in x is 1, y is negative 5. If x is 1.5, y is negative 6. When you plug in x is 2, y is negative 5. And when x is 3, y is 3. Okay, remember that the middle point in my chart is always the vertex. And the y values surrounding the vertex should be symmetric, which they are. I have 3, negative 5, and then after the vertex, negative 5, 3. I plot those 5 points. So I'm going to start with 0, 3, then 1, negative 5, 1.5, negative 6, 2, negative 5, and 3, 3. Okay, connect, try to make something that looks like a U. And we've graphed our parabola. Okay, one more example. So question number 5, again, we have our quadratic. We're going to graph. And to do that, we always start by picking out A, B, and C. A is the value in front of x squared. So here A is negative 1. B is the number in front of the plain old x. We don't have a B here. We don't have a plain old x. You can think of this as negative x squared plus 0x's minus 4. So here our B value is going to be 0. And C, the plain old number by itself, is negative 4. Let's find the axis of symmetry. So using our formula, x equals negative b over 2a. We see that x equals negative b is 0 over 2 times a is negative 1. Well, 0 divided by anything is just 0. So our axis of symmetry this time is at x equals 0. So here's our axis of symmetry. Now we create our table of values, x and y. We always put the number we just found for the axis of symmetry in the middle of our table of values. Choose 2 numbers below that. So below 0, I'm going to pick negative 1 and negative 2. Above 0, I'll choose 1 and 2. Then you plug each of those values into your original equation. When x is negative 2, y is negative 2 squared minus 4, which is negative 8. When we plug in negative 1, we have y equals negative 1 squared minus 4. or negative 5. When y is 0, negative 0 squared minus 4 is negative 4. And I know the values must be symmetric, so that means when x is 1, y must be negative 5. And when x is 2, y must be negative 8. Okay, everything is symmetric about the vertex. Okay, let's plot these 5 points. The first point goes off the graph by 1 box, but that's okay. Just estimate where it would be. The second point, negative 1, negative 5. Then 0, negative 4. 1, negative 5. And our last point goes off the graph again, but that's okay. Okay, notice that this parabola opens down. So this is an upside down U shape. Again, connect the dots. Make sure you put arrows at the ends. And just one thing that I want to point out, when you take a look at the 3 problems that we just did on the back here, notice that this last graph is the only one that opens down like a frown. I can tell how the graph is going to open based upon the value of A. If A is a positive number, positive numbers are happy. They make smiley faces, or we also say the graph opens up. If the leading coefficient, A, is negative, negative is down or a frowning face, my graph is going to open down. So before I begin, I can tell what the final graph should look like. Okay, the homework is in a second attachment within Teams. You're going to graph each of the functions and then identify their characteristics.